Okay. All right. Okay. Go ahead.
Okay, so now that we've figured that out, our next speaker is Roberto Vega. He is a PhD candidate at the University of Alberta, working under the supervision of Dr. Russ Greiner. His research focuses on how to combine machine learning with medical expert knowledge to learn accurate predictive models. He also collaborates with the local startup Meadow AI, where he works alongside their AI team to automatically analyze ultrasound images for the detection of health problems. Please welcome Roberto Vega for his talk, Technical Challenges of Using Machine Learning in Medicine. Just making sure that the slides are set up to your level. Can you read everything?
Oh, yes, it's okay. Thank you. Oh, hi, everyone. Perfect. Yes, I will talk a little bit about some of the technical challenges of applying machine learning in the field of medicine. So basically, this talk is divided into 4 main parts. I will start talking about some machine learning basics, and then I will start talking about 2 main problems that we have in medicine. And the first one is the relatively few instances that we have for training. How do we tackle that problem? And the second one is the problem of using multi-site data. Sometimes when we, and this is something that the last speaker also mentioned, when we train a model on data from one site, it is not guaranteed that it is going to work on the second one. And this is a big problem in medicine because you want a solution for the problem. You don't want a solution for one clinic who is in one corner in Edmonton. You want like a global solution. So then how do we tackle these things? And at the end, I will have a few conclusions. If you have questions in the middle of the talk, feel free to just raise your hand and ask it, or you can wait to the end. Perfect. So let me go for the first thing, the performance task and some basics of machine learning. So one of the tasks that we usually want to do is either classification or segmentation. For example, in classification, imagine that you have an ultrasound image. In this case, this is the hip of a baby. And then you input that into a classifier. And then you want your classifier to tell you if they have dysplasia or not. So this is a yes or no question. There is a second set of tasks in which you don't want like a binary or a multi-class answer. You want basically a segmentation. You want to identify something in the image. In this case, for example, this is an image of the thyroid, also an ultrasound image. And here we are interested in finding the tumors. So this is more like a segmentation task. You want to create like a mask that will tell you where the anatomical feature of interest is located. So these are 2 basic tasks in machine learning. So how do we do this? What we usually do is we start with a training data set. So we collect a lot of data and the labels. In this case, they can be images and the diagnosis. And then we input that into a learning algorithm. And this learning algorithm can be something as simple as linear regression classifiers or as complex as deep learning algorithms. It's up to you. But the output of all of this learning process is going to be a classifier. And in that classifier, the idea is that you take a new data set or a new image, a new instance, and then you get your answer. And your answer can be either a yes or no, one of many classes, or it can be like the segmentation mask. For example, in the case of ultrasound, the data set can look like this. You take an image, and then a physician, a radiologist, tells you if the image is normal or if it corresponds to a person with dysplasia. And then you collect all of this data set, the images and the things, then you input this into your convolutional neural network in this case, and then you get your output, healthy or non-healthy. So this is basically machine learning 101. This is how it works. Now, this paradigm makes some assumptions that are typically done in machine learning. One is that the data set that we have for training and the instances where we are going to apply this classifier are similar. And technically by similar, and this is a technical concept, but it means that they follow the same probability distribution. That it is a mechanism that generates these images, and it is the same in both the training and the testing. The second one is that we have enough images at the beginning to learn a good classifier. If we have only one image, well, there is not much that you can learn from it. So most of the machine learning assumes that you have many, many images and that they represent the entire variety that you can observe in reality, which is often not the case. The third one, and this is important, we usually assume that the label is reliable and it is objective. And this is a big problem in medical applications. If you show the same image to many physicians, they will arrive to different conclusions. So which one do you have to use? And you usually do not have like 100 physicians in your team. Maybe you have one or two. So you go with whatever they tell you. And in the extreme cases, the ones that are normal or the ones who have clearly a disease, well, that is easy. You can identify very quickly, or if the label is reliable or not. But the problem comes in the borderline cases, where for some radiologists, it can be, yes, this is a case of the disease, or no, this is normal. So these three assumptions that are common in most of the machine learning algorithms are often not, but these assumptions are not met in medical imaging tasks. So what are the typical characteristics of the data sets that we have in medical problems? The first one is that we have very few labeled instances for training. And by very few, I mean that we can have like a few hundred, a few thousands, or a few tens of thousands. Maybe for people in medicine saying, I have a data set of 5,000 images, that looks like something big. But compare that, for example, with the amount of images that we have in Google Images. So there are billions of images in there. So of course, Google can use very complex models to create very nice solutions because they have millions of data points. In our case, we have just a few thousand of them. To make the things worse, they are high dimensional. And by this, we mean that they are not only a few, but they have many, many characteristics. For example, if you have an image, and even if this is a small image of 100 pixels by 100 pixels, well, you have 10,000 individual pixels in there, which is a lot. Only one image contains more pixels than the number of images that you might have in your dataset. This makes the things very, very complicated. The second one is that the data is not homogeneous. They can be acquired with different scanners. And I'm going to show a few examples of this in a few moments. The other one, I already talked about this, the labels are subjective, mainly in the borderline cases. It depends on the experience of the person who is making the labels. And one more point is something called calibrated probabilities. When you get an answer from a machine learning system or for any system, it's not enough to just tell you yes, they have the disease, or no, they are healthy. You also want to know what is the degree of confidence in that prediction. It is not the same to say, oh, I believe that this person is healthy with a 99% probability, that to say, I believe that they are healthy, but my belief is 50-50 or 51-49. You want the machine learning algorithm to tell you if the answer that they are computing is reliable or not. So this is called calibrated probabilities, that this output will give you some meaning. Now, the nice thing is that we have lots of background knowledge. In general, in machine learning, we learn everything from scratch. We take a lot of data and then we let the algorithm learn everything by its own. But in medicine, we have many centuries of knowledge that we have accumulated. So how do we incorporate this into these models? So this may compensate for the lack of data. Maybe the algorithm doesn't have to learn everything. Maybe we already know what we are looking for, and then we can incorporate this into the algorithm to make it work much better. So for example, we did some experiment with these data sets. For example, we have data sets from ultrasound and glaucoma with hip dysplasia, fatty liver, and the one in glaucoma. And then we train a model using like the traditional machine learning approach. You take the data, you input that, into a machine learning system, you download a library, you push a button, trains, wait a few hours, and then you get the answer. And this is the answer that we got. For example, in the case of hip dysplasia, it was like 74%, fatty liver, it was 90%, glaucoma, it was 55%. So one worked relatively well, the other one did nothing, is garbage, the one in glaucoma. And the one in hip dysplasia, 75 is neither the best nor the worst. So now we can start applying all the things that I said before. For example, how do we deal with very few instances? And one of the things that we did is to train the model with something called a probabilistic label. And the idea is if you have a very few instances, then give me more information per every instance. So for example, we usually say that this image is a case or is a control, is normal or have the disease. And we usually encode this with zeros and ones. Tell me 0 if it is a case, 1 if it is control. What we are proposing is that instead of telling me that, we are going to train the model with a probability. So for example, this case, they have dysplasia. So 1 means, I mean, the first entry means dysplasia, the second one means normal. So you have the 1 in the dysplasia. And this is what we usually have in machine learning. So what we were proposing is instead of telling me this, tell me what is the probability of every class. For example, 60% of having the dysplasia and 40% of being a normal case. And then train the model using this information. And of course, that sounds great, but the problem is, where do we get this information? We usually do not have it. If we ask the physicians to tell us like their estimated probability, people do not think in probabilities. What does 60% mean for a physician? What 75% means? So this is where we start leveraging the medical knowledge. For example, I don't need a machine learning algorithm to interpret the entire image. I know what we are looking for. For example, in the case of hip dysplasia, we look for 2 key features of the image, something called the alpha angle, that is the angle between the ilium and the acetabulum. And the second one is something called the coverage. That is basically the ratio of D1 over D1 plus D2. So it might mean something, it might not mean anything. The thing is that the physicians or the radiologists use these 2 conditions to diagnose the disease. And we already know that. So then what we did, don't pay attention to the ugly equations, is we built something based on probability to compute that. And let me tell you how that works. For example, you have this image, and the physician told you that they have dysplasia. Then you go, and then you measure these 2 quantities manually. This is done during the training phase. You manually go and take your ruler and your, I forgot the name of the device or the tool for measuring angles, but then you measure the angles, and then you measure the ratios. And then it turns out, for example, that in this image, the angle is 41, and the ratio is 0.23. And then you go and then you build your table or your graph or whatever you want to call it, and then you put your point there. Angle 41, coverage or ratio 0.23. And then you repeat the same for all the images that were classified as dysplasia. So now you have a set of points in there. Then you do the same for the normal people. The people whose hip was classified as normal, well, you take them, you make the measurements, and then you compute those things. Then you put something called a probability distribution on top of that. If you are familiar with this is a Gaussian probability distribution. If you are not, just identify that we have like 2 sets of ellipses, and each one has a center. The probability depends on how close you are to each center. That's the easy way of looking at this. The thing is that we can compute the probability per every image. For example, we take this image, we see where in the plot it is, and then we can calculate that the probability is 97% of having the dysplasia and 3% of being normal. And then you do this for every image, and then you can train the system. Now, the important part is that this measurement has to be done only during the training. Once that you train the network, then you just take your image, You input that to the network, and the network will give you this probability automatically. You don't have to measure anything anymore. So you train your network again. Does it make a difference? It does, because with the same amount of data, for example, in hip dysplasia, we went from 73% to 83%. So we improved 9% only by making this small trick. In the case of fatty liver, it says 90 and 89. It looks like we lost, but nah, it's just rounding error. It's basically the same, they are tied. And in the case of glaucoma, we went from something that it is basically garbage, that it is 55% to 77%. So just by incorporating this extra knowledge, even in this small data set that contains just a few hundred images, we were able to boost the quality of the predictions. Now, this cannot be done in all the cases. There are cases where everything is more difficult to establish. For example, in here, segmentation. Segmentation, you can think about that as pixels-wise classification. So again, imagine an image that it is 100 by 100. When you want to make a segmenter, then you need to give a decision per every pixel in that image. So go pixel number 1, is this part of the tumor that you are looking for or not? Then pixel number 2, then pixel number 3. So then you have to do this like 10,000 times, once per every pixel, until you get the desired mask. Good luck trying to go manually for every pixel in the training set, trying to determine the probability. No, that is not possible. So we cannot use the probabilistic labels here. It is not clear how to define the expert features either. How do you determine what is a tumor or not? And most importantly, how do you compute that? For example, if you ask a radiologist what determines a tumor, they can say, oh, the texture is changing from the normal tissue. That is perfect. And then we can see that with our eyes. But how do you code that? What does texture mean? How do you detect the changes in texture? So that is more complicated. The typical approach is, again, a deep learning algorithm. You take the image, and then you have the segmentation mask. And then you learn an algorithm that, given the image, creates the segmentation. Now, there are more ways of giving extra information to the system. For example, maybe we only care about identifying the thyroid. But what if during training, we give more information to our network? For example, we can tell them, well, yes, you care about the tumor, you care about the tumor, which is the purple mask in there. But I'm going to tell you some extra things. For example, the thyroid. This thing in red is the thyroid. This thing in cyan is the trachea. And this thing in blue is the carotid. So now you have to identify everything. I just care about the tumor. But now I give you this more information. So now we train, and now we have like a multi-class problem. The change is trivial. You just have to give more labels. And where do we get these labels? You just have to take an anatomy book, and they will let you know what is in that image. For example, this is the ultrasound, and then they tell you this is the trachea, this is the thyroid, the left lobe, right lobe, the isthmus, this C is the carotid, and this JB is the jugular vein. So you get them from there, and then you go and then you can label them. Now, why do we want to include these more classes? The first one is, intuitively, it makes sense because you are giving more information to the image, and then you are teaching anatomy to your network, whatever that means. But there is also some justification from the literature. For example, they say that training instances for good generalization means that it will work well when you basically use it, linearly decreases with the number of tasks. What does this mean? That if you have more tasks that are relevant, then when you make a classifier that has to perform well across all of these tasks, it will work better. Again, let me put this into the picture in here. We care about segmenting the tumor in there. That is one task. But I'm going to give you 3 extra tasks. also detect the carotid, also detect the trachea, and also detect the thyroid. So now you have 4 different tasks. And then there is literature that tells you if you give me more tasks and they are related, then I will perform better. The second one is that learning common features might decrease the overfitting. Some of these things have many things in common. From preliminary experiments, it also works. I don't have the numerical results with me, but the segmentation works much better when you do this approach. And one intuition is that this might rule out some explanations. For example, you have this image. This ugly image from here is an ultrasound image of the thyroid, and maybe it doesn't say anything to you, which is fine. You don't have to understand what is there. But this is a thyroid nodule. That ugly thing in there is the tumor or the nodule that we are looking for. Why not that one? Well, that one cannot be a tumor, it's the carotid. Now, there are some tumors that look just like that, but they are in a different position. So it is important to distinguish if something is an artery or a vein, or if it is inside the thyroid and therefore can be a tumor. What about this thing? This thing looks very similar to the circle in green. I mean, visually. Well, it cannot be a thyroid tumor that is not even inside the thyroid. So then giving this extra information can help you to rule out some of this explanation. Let me give you a simpler example. Take the image on the left, where you have cases and non-cases. And imagine that you want to draw a line that separates the orange from the blue. Well, the best line that you can get is something like that, right? This is the one that separates the best things. You can create one line if you have 2 different classes. What if I tell you that the blues are not the same? That it is blue and it is green. Then you are allowed to have 2 lines because now you have 3 different classes. So now you can distinguish them perfectly. So this is the intuition behind giving this extra information. And it works, it's nice. The third one, the multi-site data. Let's imagine that we want to build a segmenter again. We have this input, again, an image of the hip. We input that into a segmenter, and then we want this output, a mask that tells you what is the ilium and acetabulum, that is the red bone, and the blue bone, which is the femoral head. You want to do that. So you take your training data acquired from a Philips scanner, but then you are going to use it on a different clinic that has a Toshiba thing. So you take your training in Philips, you make everything, then you test it, and then you say, wow, this is amazing, it is working. Look at this segmentation, it's beautiful. So now you go, and then you test it on the Toshiba. Ta-da! It is horrible. What happened? This is trivial for anyone. I mean, for example, if I tell you that the red bone, well, what is the red bone and the blue bone, I am sure that most of us can see the same shapes in the images on the left. We can see like the big circle, and then we can see the bones that are in an angle. So why is the network giving this output? So this is because of the problem of the distributions. It is not the same to train on images from one scanner and then test it on images from a different one. This is called batch effects. This is called domain adaptation. It's a problem that we are studying, but that it is very relevant in medicine because you don't want an algorithm that does that. Or imagine that you have one, even if you have only one clinic and you have 2 different probes, I cannot tell you, oh, well, guess what, use only the Philips one because it will not work anywhere else. Well, nobody wants that. So for example, we are experimenting with a few nice things. I don't know if you have heard about style transfer, but the idea is like this. Take a picture, any picture from the left, like the one in the left, and then take a piece of artwork, like the one in the middle. Then you can combine them. You can transfer the style of the picture to the picture, well, the style of the painting to the picture on the left, and then you get that beautiful thing on the right. What if we do something similar in here? For example, we take the Philips image, and that will determine the content. Then we take the style image, that is one image from the Toshiba dataset, and then we transfer the style from one to the other. Does this work? It turns out that it did. For example, before making the change, the same algorithm, the same data, just making the style transfer that is the only difference. When you get the input of the images on the left, then you get the output on the middle. But if you do this simple style transfer to make the images look as similar as possible, then you get the output on the right. None of them is perfect, but correcting the images or the segmentation on the right is very simple from the computational point of view. In a post-processing, we can fix these empty spaces. Good luck trying to do the same on the image on the left, the image on the middle. Sorry, they are messy. The prediction is basically unusable. The images on the right, now we can work with them. So this is one of the many tricks that we can do. But the important thing is that we have to acknowledge that we have this problem, and then we need to start, well, to continue making research to do that. Now we also have the numerical results. You don't have to care about this, but in identifying the red bone, we went from 44% to 64, so we have a 20% improvement, and in the femoral head from 80 to 87. This is something called the DICE score. If you don't know what is that, don't worry about it. Just know that 0 is terrible, 1 is perfect. And everything that is above 0.6 is actually very, very good. So we are very, very good. So the conclusions is that the medical data often violates the common machine learning assumptions. And there are some ways to improve this performance, and we have to acknowledge what are the assumptions that are being violated. So we can provide more information per every training image, and to do that, we can leverage on the medical knowledge that we have. We can try to correct for discrepancies in the training and the test distributions. I showed a very simple trick right now, but there are many ways of trying to accomplish that. And this is, for example, one of the key things that we do at Medo. In Medo, we analyze ultrasound data, and this is one of the key things that allowed us to create the first product that is already on a few clinics, diagnosing dysplasia. How do we minimize this discrepancy? So that's it. If you have any questions, I will be happy to take them.
Thank you, Roberto. We have approximately 2 minutes for questions. So any questions, please line up at the microphone in the center. And any questions from the online attendees, please put them in the chat. Thank you.
Hello, Roberto. I can kick us off with a question from the chat. This one reads, you talked about some common assumptions that are not always true for medical applications. What do you think physicians and healthcare professionals could do to make those issues less challenging?
Well, I think that we need to do some research in how to incorporate the medical information that we have into the machine learning systems. So, for example, I acknowledge the use of things like deep neural networks, but they are very limited when we want to incorporate extra knowledge. So I like a lot the probabilistic approaches that can have deep neural networks in the middle, but at the end of the day, they can incorporate very quickly or very easily extra information. So I think that we need to move to something that is less black boxy and that will allow you to incorporate this extra knowledge. Probabilistic graphical models is a tool that I really, really like. And yeah, that is one of the things that come to my mind. Oh, and talk with each other. We cannot have like the physicians in one side and the computing scientists in another. No. One of the keys for solving these problems is that we have sonographers and physicians next to us explaining and communicating what are the things that we are looking for, how do we identify them, and then we start putting the code into that.
I think that gives everyone a little bit more to think about. Quick correction, we have more than 2 minutes for questions. So
okay.
If anyone has questions, please do come up. But next question, that's the next question. What do you do when testing instances are generated off policy, as in generated by a different probability distribution than the one that it was trained on?
Yes, so we have to make a few assumptions in here. And the first one is, even in these cases, there are things that make the the images different. For example, you can see that one is conic, the other one is not. One seems to be like more blurry, the other one seems to be like more well-defined, is more sharpened. So these two things come from different probability distributions because they have two different properties. Now, in both of them, we as humans can distinguish the two different bones, the circular bone and the acetabulum and the ilium. There are these two. That means that there is a space where they are similar. So what we have to do is we have to find a mapping between these images to a common template. For example, if we could somehow create a mapping from this to these lines or to a simpler space, then we eliminate the things that make the images different. This, of course, is not trivial, so there is a lot of research. But one of the strategies that we follow is how do we take the images and convert the images into a different space where in this space they are equivalent. And again, I might go a little bit technical in here. That is called divergence. Divergence is the difference between two probability distributions. So there is a lot of research in how to transform this image into a vector. And then how do you minimize the discrepancy or the divergence between the vectors of the images from Philips and the vectors in the images from Toshiba. So you can do this automatically, you can do this with feature extraction, but the idea is how do you map them into a common space? And then you learn your segmenter or your classifier in that common space. When you receive a new image, the first thing that you do is you make further transformation and then you apply the algorithm. So that is one answer that I can give.
I was wondering about the style transfer.
Yes.
If presumably you're changing the original image, so yes. What are the risks are there any risks of losing some of the diagnostic information?
Yes. You're right. That is very important. For example, there are some technical definitions of style transfer. And basically what you are doing is you are putting the texture, whatever that means, from the style image into the content on the other one. In this case, style transfer works great because what we are trying to identify is basically two different structures that is part of the content. So you can see that there are two geometrical lines for the bone and one circle in here. So the texture is irrelevant. So if you modify the texture, you are not getting rid of the information that allows you to do the diagnosis. Where this is going to fail, for example, you cannot use style transfer in detecting tumors because the tumors are a difference in the texture. So if you remove the texture, you can artificially remove the tumor or you can artificially put a tumor in there. So they have their scope of application. These are not universal solutions. So answering your question, is there a risk that will happen? Yes. So I will recommend to use style transfer when texture is irrelevant for the diagnosis. That is something that happens in hip dysplasia. That is not something that happens, for example, in the identification of other things.
Yeah. Okay, we still have time for a few more questions. Another one in the chat. What do you think is the reason glaucoma? Is it pronounced glaucoma? It is pronounced
glaucoma.
Glaucoma. What do you think is the reason glaucoma picture classification performs worse using different algorithms?
Okay. In this particular case, it's because the data set is extremely small. We had like 100 images, 50 from glaucoma, 50 from normal. When you imagine that you give any person, you take one person randomly from any department at the U of A, and imagine that you don't pick anyone from medicine. And then you give them 100 pictures of the eye, and then tell them classify what is glaucoma and what is not. Well, they are going to have like a very challenging task if they only have like 10 images, and then you present images that they have never seen before. The same happens with the computer. The data set was very, very small, and this is what made the performance terrible, like 55% in this case. What we did is we told the algorithm what do they have to be looking for. For example, we told the algorithm you have to be looking for the difference in this circular thing. Oh, you cannot see it here. Okay. In the middle of the picture of the eye, there is like a bright circle. So then we were coding that into the algorithm. So they were looking for that. We made the task easier. That is the difference in this case. Yeah.
Okay, I think we have just enough time for one last question. What do you think about making use of multiple different AI algorithms as a pipeline? For example, could we have an algorithm that learns from a medical textbook and feeds into another algorithm that classifies images based on the results from the first algorithm?
Yeah, you can definitely try it and see how it works. If it works, it's great. What do I think about that? I think it's a good idea. I mean, that is definitely worth exploring. We have to be careful though, because those things are very difficult to debug. When you have many algorithms, and each of the algorithms is very complex, when something fails, it's harder to identify what is that going to fail. But I mean, go ahead and try it. And if you can show that it works, that is perfect. You know, one of the important difference is that in medicine, it matters if you make a mistake. Many of these combinations of algorithms work great for companies like Google, like Facebook, Netflix. But if Google gives you the wrong advertisement, nothing happens. If Netflix suggests you to watch a movie that you don't actually like, well, nothing happens. If you give the wrong diagnosis, things can happen. So in this case, we have to be very careful in the algorithms that we use, and we have to be sure of what are the algorithms doing that we can rely on their predictions. So if you have many complex algorithms in one pipeline, then that becomes a little bit more obscure. That doesn't mean that it is not possible, but you just have to be careful.
Well, thank you. Yes, thank you, Roberto, for the very didactic overview of all the challenges that come with ML. First off, a round of applause, everyone.
Thank you.